It's a pleasure to welcome Kimya Khetarpal today. She's a research scientist at Google DeepMind. She earned her PhD in computer science from the Reasoning and Learning Lab at McGill University and Mila, advised by Doina Prekup. She's broadly interested in AI and reinforcement learning. Her work has appeared in leading AI journals and conferences such as NeurIPS, ICML, AAAI, and many others. Her work has been featured in Technology Review, and she was one of the rising stars at EECS in 2020, among other honors. So looking forward to your talk. Thank you for being here, Kimya.
Great, thanks for having me here, and welcome everyone. Today I'll be talking about bridging state and action, an attempt to go towards continual reinforcement learning. And just a caveat, there are not going to be any videos with robots running around doing awesome stuff, which is where I'm hoping to collaborate with many of you as I'm based here in Seattle. So while with a lot of promise from AI, what would we like AI agents to do for us? So consider this sequential decision-making problem where the robot has to navigate through the kitchen, find and fetch a beverage with a healthy snack. Now the problem at hand for this robot concerns with a very large state space due to a high dimensional observation space, that is of pixels, where with every time step, the robot has to it involves the robot to making a large number of action choices, resulting in a large branching factor. With the need to reason and plan across many long temporal horizons. And all of this is especially challenging in the low data regime, by which I mean that the number of interactions that the robot might have might be limited. Now to do this successfully, an AI agent needs to process the stream of incoming data by selectively paying attention to parts of the large state space. So for instance, the robot would need to attend to the empty space in front of it to navigate closer to the kitchen island before even it can do any other task. Secondly, it also needs to reason and plan across the large space of temporally extended action choices referred to as options. For instance, all possible action choices or options spanning various timescales would be really large space to reason from. Next, it should be able to predict long-term effects of its actions. So for example, it needs to predict the successful picking of an object to be able to do this task successfully. Moreover, the robot should be able to understand the action opportunities in each scenario. That is, it should know which states afford which behaviors in the context of the task at hand. And while it is affordable to pick all these objects from the state, the system must continually adapt to non-stationarity in the environment as new affordances might present themselves. For example, the apple in this case, which is a very viable candidate for a healthy snack to be found and fetched. So how can we get there? To this end, my research goal is to enable RL agents to represent the world knowledge efficiently, to be able to plan with it, and to adapt to changes over time. And to do this, my work has been focused at the intersection of three key pillars, that is selective visual attention, representations of temporally abstract actions, and grounding learning in intuitive theories of affordances, all building towards the goal of continually learning agents. In this space, my contributions has been as follows. At the intersection of selective attention and temporal abstractions, my work included learning and leveraging attention mechanism to discover specialized skills which have spatial specialization such that it allows it to adapt faster in the presence of non-stationarities in rewards. Alongside constructing value-preserving state action abstractions, at the intersection of temporal abstractions and affordances, I proposed temporally abstract partial models that I'm going to talk about in the second half of the talk, and studied the characterization of affordances as hard attention in a hierarchical reinforcement learning system. Taking inspiration from computational models of human visual attention and cognitive psychology, at the intersection of affordances and selective attention, I present a framework that enables AI agents to represent and reason about the world through the lens of affordances. And finally, moving towards the goal of continually learning agents, I wrote a technical review and perspectives, and in a follow-up work, show that as the agent acquires more and more knowledge about its environment, the agent should be planning with increasingly growing horizons, leading to better theoretical guarantees. Today, in the first part of the talk, I will first discuss this particular work on a theory of affordances in RL. Humans undeniably possess a very general sense of intelligence. Both people and animals understand the relationships between the features of their environment and the actions that are feasible in those features. For instance, both babies here and animals know it is affordable to crawl on a rigid surface despite the surface being a wood or a carpet. Gibson coined this term affordances in 1977 to describe such relationships in the context of embodied agents acting in a physical world. To this end, I will now present this framework that enables AI agents to represent and reason about their environment through the lens of affordances. I tackled this problem in reinforcement learning. In reinforcement learning, the agent-environment interaction and therefore the learning problem is formulated as a Markov decision process. A Markov decision process comprises of a state space, an action space, a transition distribution, which tells you in which state and action where you will end up, and a reward function. Most prevalent RL agents today mostly failed in real-world situations because they do not have this general understanding of which actions are feasible in which situations. Many RL algorithms assume that all actions are always available to an agent. However, not all states afford all behaviors. So for instance, the robot arm here tries to pour the milk into the bowl even when the bowl is not directly located below its arm, and hence it is not affordable to pour in all these states. So if you're wondering why should our agents care about affordances, there is some motivation that I'd like to give about it. So understanding which situations afford which behaviors has many potential benefits. For instance, it will allow RL agents to generalize better by capturing the underlying invariances in which state affords which behavior. For example, it is affordable to pick up a banana in both these states due to the invariance in its position and the robot angle at which it is located, despite other distractors in this state. Next, if our agents are able to understand which states afford which behaviors, it has the potential to facilitate faster adaptation in new scenarios with the similar dynamics of the world. For example, it is not affordable to walk into walls or kitchen, despite where the kitchen is located or which kitchen you are in. And finally, understanding which situations afford which behaviors will allow to build partial models of the world which are much more compact and sparse and therefore will enable faster planning. In this work, I ground learning in affordances for faster planning and more efficient learning of these world models. The key contributions of this work are that we formalize action success via the notion of an intent. We define affordances in MDPs as states and actions that complete those intentions. We quantify the planning loss bound determined by the size of affordances. And finally, we propose a data-driven approach to learn these affordances and use it to estimate a transition model. So while a lot of these can be directly studied in robotics, let us first try to establish these fundamental ideas in a simple two-dimensional environment, with the main goal to bridge the gap between theory and practice. To give some intuition of what an intent is, let's look at this robot in this two-dimensional grid world. An intent is best captured by thinking about a target state distribution that we would like to be achieved with an action. For example, consider this robot in this grid world and consider the intent of going left. The intent to successfully go left is then best captured by thinking about a target state distribution that we would like to be achieved with the action left, denoted here by the gray states. So given an MTP and an action A, an intent is best captured by this desired state distribution that we would like to be obtained when executing this action A. An intent is satisfied to a certain degree if and only if its distance from the true distribution in the world P is bounded in some distance metric. Now, having established the notion of intents, we built the notion of affordances with the goal of restricting the state action pairs so as to allow intents to be satisfied. So going back to this intent to go left, affordances are then defined as subset of states and actions which complete these intents to go left, which are denoted here by the states and the corresponding arrows. We now propose a data-driven approach to learn affordances. We use the standard cross-entropy objective to train affordances, where we will represent the affordance as a classifier A parameterized by theta, which tells us whether a state and action can complete an intent. We assume that we have access to an intent completion function, which tells us if an intent can be completed using a particular state and action, which now becomes the target for classification. Transitions are collected from the environment, and their intent completions are evaluated to create a dataset D. In the experimental setup, we consider a two-dimensional continuous grid world with walls that are not possible. Action space is the displacement in the x and y direction, and intents are simply navigational intents that include change in any of the four directions. So move left, move right, move up, or move down. We then evaluate the learned affordances. For instance, let us evaluate the probability of completing the intent to move right. And in particular, let's look at this particular action that applies a diagonal displacement, moving it in the positive x and y axis. We visualize a heat map showing the probability of completing this intent at every state in the environment for this particular action of diagonally going in the positive direction. Note how the classifier is able to correctly learn that the action cannot complete the intent near the walls. Using the same approach, we can also learn the affordances for multiple intents simultaneously. For example, the heat map to go down or left shows that in no state can the positive diagonal action complete the corresponding intents. Next, we ask the question, what can we do with these learned affordances? One potential route is to learn an affordance-aware partial model that I've been talking about that is more robust and hopefully captures the invariances and generalizes better. We use a Gaussian generative model to estimate the transition dynamics. To obtain a baseline model, we maximize the log probability of the next state transition. But then, to train an affordance-aware model, we use the outputs of the affordance classifier to simply mask the loss for transitions which do not complete any intent. So the idea here is to only model things that are relevant in the world, such that you will end up with a partial model that captures the things that are relevant in the world. To analyze the empirical behavior of the agents, we look at it qualitatively. Let us consider an agent in this state near the wall which applies the left action as denoted by minus f of x. We note that the baseline models predict an incorrect or offset transition distribution denoted here in cyan, whereas the true Gaussian Gaussian model is denoted here in gray. Model for the left action is not aligned with the environment model. In contrast, the affordance-aware model generates near-perfect predictions, correctly estimating the next state distribution in this particular state and action. Let us now look at a more interesting example of the right action which the agent applies in this position. For the right action depicted in magenta, it is not possible to go into the wall. We note that the baseline model distributes the mass of its predictions evenly along the wall, which is incorrect as it is impossible to go through the wall. On the other hand, the affordance-aware model first uses the affordances to determine if this action can complete any intent. And in this situation, since it cannot complete any intent, the transition model is never queried, and it's a partial model. So affordance model does not predict anything for the right action, since no intent can be completed. So intuitively, the baseline model, when you're trying to model everything in the world as a full model, it has many edge cases, and it's a much difficult rule to capture. Whereas the partial model, which is informed via affordances, has an easier job and a simpler rule to learn of what's affordable, as opposed to a full model. In summary, in this work, our goal was to lay the theoretical foundations of intents and affordances in reinforcement learning. Affordance-aware partial models led to improved generalization and robustness to out-of-distribution actions that were not seen in the training distribution.
Well, question. In your case, the affordance is either achievable or not achievable at the wall. And so as a consequence, you're able to filter out things that don't happen. But imagine you had a squishy wall, like something where you could poke into it a little bit, but not a lot. In situations like that, is there, everything is possible, just to varying degrees, so it's not either yes or no. Where does the math, allow that? I saw an epsilon. Is that
Yes.
what it captures? Is that what the epsilon captures?
Yes, so there's an intent satisfiability. That's a very great question. And there's an intent
Okay.
satisfiability criteria of how much do you want the intent to be satisfied up until. So you're right. So let's say you met with you have a P that is the true dynamics of the world, and your intent is saying that I will only consider it if it meets to a certain threshold.
But you don't have access to that when you're learning, right? So how do you...
So that's a hyperparameter,
That's a hyperparameter,
right?
I see.
Yeah.
Okay. I see. Okay.
Yeah. So what does this imply for the general audience that might or might not do RL? So it's just telling us that RL agents can build one-step transition models which are affordance aware, and understanding what is affordable where helps the agent in new but similar situations. So the agent in our case did not see all possible actions being near the wall, but it is able to generalize to new instances and new actions that it has not seen, simply because it's able to capture the invariances of what transfers across many different situations of what affordances are. So recall this scenario of a mobile robot that has to perform this long horizon task. And recall that the agent has to process this stream of incoming data by selectively paying attention across many different timescales. So affordances are telling us and informing us of all the feasible actions in a given state. But to see the effects of these actions in the world, we would like to build partial models, not just single step, but across many different timescales, which can capture the effects, long-term effects or consequences of an temporally extended action or an option. So in the second half of my talk, to reason and make predictions about many different timescales, I'll talk about my work on temporally abstract partial models. So much of the existing literature considers single-step models, which can be very challenging to learn as it accumulates error and has a compounding effect of those errors being accumulated more significantly. Many works consider model-based RL, but the models are being built over entire state and action space, making this process really intractable. And finally, learning and planning with options or temporally extended actions that apply everywhere is very counterintuitive, because they do not have any spatial specialization. So for instance, you'll not apply a skill of picking up this glass when this glass is not present in this state. With a few notable exceptions of George Kondiaris' work, which considers this notion of preconditions, actions, and effect, but they deal with PDLLs and stuff. As we discussed earlier, building internal models across many different timescales has multiple potential benefits, such as it would allow faster planning, faster learning, more efficient planning, and especially allow our agents to make predictions across many different timescales in the future. To incorporate temporal abstractions or temporally extended actions, I work with the options framework. Options are expressed in terms of the state and option space, analogous to the state and action space, alongside option transition models and a reward function. For example, the option to drive forward is formally expressed as a triple consisting of an initiation set expressing where this option can be applied, the option policy suggesting what actions to take during that option is being prescribed to, and the option termination indicating where to end the option. This provides a nice way to reason across many different timescales where options can now be of different durations. The key contributions of this work are that we extend the option models to account for affordances. We establish a theoretical understanding of the trade-offs associated with using options or actions jointly with affordances. And finally, we empirically demonstrate end-to-end learning of affordances and partial option models in a function approximation setting. So let's start with the key concepts. In the previous work, I formalized affordances in RL by considering the desired outcome of a primitive action, that is, the intent associated with one-step action. We will now generalize this notion of intents for options, which can be achieved over the duration of an option. To do this, we will consider the classic taxi domain, where the taxi here has to pick up the passenger and drop them off at one of these destination cells. Specifically, we now consider the desired outcome of an option, that is, the intent associated with a temporally extended action. Formally, a temporally extended intent of an option O specifies the probability distribution over the space of the trajectories, which describes the intended result of executing an option O in a state S. So the associated intent model is denoted by the probability of an option trajectory given a state option pair. An intent here is then satisfied to a certain degree if and only if the distance between the intended probability distribution and the true option distribution is bounded in some distance metric, and in our work we use the total variation metric. Note here that the options are a full space of trajectories. So you can imagine all possible trajectories that you can take of many varying lengths as the potential choices that a robot has, which is a huge space to work with. Intents here, on the other hand, are desired long-term consequences of the trajectories. For instance, in this case, intents are chosen to be these destination cells, or the states where the passenger needs to be dropped off. So now, given a large space of options and well-defined temporally extended intents, for example, specified as the destination states here in the taxi domain, option affordances are defined as a subset of the state option pairs such that for all states in option, the intent associated with that option has a particular degree of satisfiability. So for instance, in the taxi domain, while there can be many large space of options possibilities, given the intents to drop off at destination states, affordances are subset of the state option pairs which meet this intent. So the gray arrows here denote unaffordable options that do not achieve the intended effect of executing those options, whereas the black arrows here are representative of some of these options that meet the intent satisfiability criteria. So now we'll discuss key theoretical results. And one thing that we are really interested in studying is the ability to be able to plan with these options. To study this planning loss, we consider the certainty equivalence control setting. So in this setting, the agent is going to act according to the policy that is optimal with respect to its estimated model. So we know that we have an agent that's going to build a world model, a transition dynamics model, here denoted by M hat AFI, and it's going to do its best, so the pi star with respect to that estimated model. But at the end of the day, it's going to be evaluated in the true MDP, that is M. So we are interested in providing a bound to this loss, where we are looking at the value of the true optimal policy with respect to the value of the certainty equivalence control policy, but still being evaluated in the true model, that is the ground MDPM. So the planning loss is bounded by the following term as already established by Nanjiang and colleagues. Introducing temporal abstractions bounds the planning loss by the size of the state option pairs and the corresponding policy class. However, note that this space can be really huge due to the combinatorial number of sequence of actions that are possible in each option, and because the policy class here has an exponential space. Therefore, it is even more important to reduce the planning complexity at this abstract level that we care about. Our work incorporates affordances in temporal abstractions, resulting in the following bound. So the planning loss now is primarily bounded by three key quantities: the accuracy in the approximation of the intent, and the size of the affordable state option pairs or the affordance set size, which also determines the SMDP policy class, all of which now introduces a trade-off between your approximation error and your estimation error. So there is an approximation error because we are considering certain intents, and which will tell us how far we are from the reality. So if the intents are completely misspecified, we will incur a huge intent approximation error. But let's say you had really well-defined intents and you have managed to solve that problem, then you can have much faster, you can have much lower intent approximation error, and your error source will mainly depend on the amount of data that you have seen. So as a result, the agent can perform faster planning across many different timescales, though at the cost of a potential approximation bias due to the inclusion of intents. So maybe to stare a bit at this bound for a second.
I had a question about the bound, but I think you might be able to answer that. Go on,
Okay.
I'll ask after you.
So basically, what I was going to say is that just to delve deeper into the bound, if you have intents which are well defined and you don't have a huge intent approximation error, then you're really building, remember you're building this model P hat of the environment transition dynamics. So now there is a bias variance trade-off where you have controlled the bias, but there is going to be a variance on how much data that you have seen. So really it is a low data regime where these results will shine a lot, because if imagine you had any amount of data, in the limit it doesn't really matter, you will be able to figure out the whole model of the world and you'll be fine. But you don't really have limitless data, and you will always be in a low data regime, especially if you're dealing with robots and real world environments. So it's really going to be an intermediate value of this affordance set size, where you'll see the, I don't show them here, they're in the paper, but you'll see nice U-shaped curves which will indicate that there's an intermediate value of affordance. So let's say if everything becomes non-affordable, then you're going to have a huge bias because that's not the reality. Or nothing is affordable. That's again not the reality, and you will have this trade-off that you have to manage, and there will be an intermediate value of what's affordable. And once you know that, then you will be at the sweet spot in the low data regime where you'll see the most gains by planning with this kind of setup. Yes?
Yeah, I think I was going to say that like it's very hard to shuffle complexity from one to the other. I mean, your point of like the sweet spot, I'm trying to understand, like not all planning problems will allow you to be in that sweet spot.
Mm-hmm.
And like there may be certain planning, unless you think that's not true. Because it depends on the definition of your affordances, depends on the definition of your intents. So I'm wondering, like as an extremal limit, right? Like you're a rat in a maze, and your affordance is I'm going to get out of the maze. Well, that's not very useful,
Mm-hmm.
because then like it's still intractably hard. So I'm trying to understand, like I like the idea of the U-shaped curve, but like among problems that exist, like where do they fall in the curve? Or you could also say that that's not true, that like every problem can be reconstituted in such a way that you can create the affordances and the intents automatically, or even by a human,
Yeah.
to be more data efficient.
I think like there'll be quite a few problems that will still fall under the low data regime where you'll see these gains. Maybe, for example, if we take the example that you gave, like the rat has to just get out of the maze. So that's like a high level task, I would say. Like, yeah, it's like a task where you might not even need temporal abstraction for that matter. So I'm imagining tasks which are, let's say, complex enough and large enough, but at the same time that they do need this low data. I think there'll be enough tasks that'll fall under this sweet spot. But I think there's an implicit assumption, maybe that's what you're alluding to, that here the kind of results which I'll show and which I showed before will assume that somehow your intents are really well defined. Yeah. And they are related to the larger task at hand. Like if they were completely misspecified intents, then you cannot get the system working with stability. You will have to do an intent revision round, and you'll have to do a two-phase process of somebody specifying a misspecified intent, and you go back. So we have this assumption implicitly that the intents are well defined, which here I'm clearly elucidating that there will be an issue if you're not well defined, but also that they're related to the high level task. Otherwise, you're going to be completely divergent. Like in your case, for example, maybe the intention is directly the task. Yeah. So, yeah.
I see.
Yeah.
So is what you're saying just that like this can get you benefits if you have good priors about the structure of the environment? And have you thought about like if you have like some like offline data about like your situation, like how you would actually sort of quantify the intent approximation if you were learning from that?
So here we assume that we have access to intent. With the experiments that I'll show you, we assume that we have access to intents which are clearly available from the like navigational intents. Like it's like by default going to be there, or information seeking intent. Like we don't have to really hand design it, but it's just there for free, right? But we are assuming, so in your case, if you have offline data, you can easily model long-term temporal abstractions out of it, but you won't be able to, you can get intents for the kind of, by making prior assumptions only. And if you're saying how to do that problem of not assuming any structural knowledge or any prior, then you are into an intent discovery problem, which is equivalent to a sub-goal discovery, which is basically asking the question, where do rewards come from? So you're back in the chain of like very open problems. Whereas there can be many, many cases where you have very readily available intent, like from a user in the loop or other ways of domain knowledge and so on. Yeah.
Is there an inherent connection with intents over options and like sparse reward structure, or not necessarily? Like, so if you can be very sparse about the way you're describing reward, does it always map to this?
Yeah, that's a very good question, because the original motivation for us to do these intentions is that somehow you've managed to discover really peaked states, like where the information really maximizes, and you only care about those, and you only want to build a model of the world over those states that are really important, like bottleneck states or hallways or stuff like that. We haven't quite solved or even addressed the intent discovery problem in this work, but that's the whole motivation behind it. Yeah, to be very sparse, but still be abstract and useful enough that you have enough information in your models.
Should we hold the remaining questions till the end? It seems like we might get stuck.
Sure. Okay, so to build the transition model, so let's look at some sample complexity results. To build the transition model, transitions are being estimated by sampling a simulator in our case, with the number of calls to this simulator referred to as sample complexity. So modeling one time step dynamics would require samples in the order of the magnitude of the entire state and action space, which is a very well-known fact. So our solution is to construct temporally abstract partial models where sample complexity, where we are mostly interested in studying the sample complexity of an epsilon optimal estimation of the action value function, while given only access to a generative model like a simulator. So existing work has shown that an action value-based variant of value iteration called Q-value iteration finds an epsilon optimal estimate of the action value function with high probabilities using samples proportional to the state and action space. There is a modulo operator missing for A here. However, with large state action size, this can be really intractable, as we know. So using options allows us to get the similar estimate at the SMTP level with samples proportional to the size of the state and now the option space. But remember, as I mentioned earlier, even this can be significantly large and in practice really challenging to access to these many samples. So to cope with this, we propose building this partial option model instead, which allows us to get the same estimate of the option value function using samples which are now proportional to the size of the affordance set size. And remember, this is the set size of affordances can be easily controlled by carefully specifying intents or making your intents peaked and sparse in certain target state distributions. So this provides the ability to our agents to understand action opportunities, resulting in improved sample efficiency if you're building a partial option model. So in the final segment, let us look at the empirical impact of learning affordances and leveraging them to learn partial models for planning. So again, let's consider the 5x5 taxi domain here, where the taxi must pick up and drop off the passenger to one of these 4 destinations denoted here by red, blue, yellow, and black states. There are 6 primitive actions: up, down, left, right, pick up, and drop, and 500 states which are represented as simply one-hot encoding. And the agent gets a reward of -1 for the amount of time it takes in solving the task, a reward of +20 for successfully dropping off the passenger, and -10 for dropping them at the wrong location. So let's look at the experimental setup. We have a set of pre-trained option policies, all of which are including go to a particular XY location, or drop off at a passenger at an XY location, or pick up the passenger at an XY location. We define intents to be passenger-centric, which includes drop-off at any of the destinations, as I mentioned earlier. So rollouts of the pre-trained options are used to collect the transition data. We then use this transition data to learn linear option models to predict the next state distribution, the option duration, and the option reward. Affordances can be incorporated in model learning to mask the loss of unaffordable state option transitions, therefore leading to partial option models, which can then be used for planning over options through approximate dynamic programming. In our case, we use approximate value iteration and obtain a policy over options. Affordances can then be incorporated into planning by only considering state option pairs that are affordable in the affordance set. We report the success rate, that is the proportion of the episodes in which the agent is successfully able to dropping off the passenger at the correct location. So all nodes in this pipeline happen asynchronously and simultaneously. So first, we try to answer what is the impact of affordances set size on the performance. So during evaluation, we report the success rate versus the training steps, and through the threshold, control the affordance set size. So higher the threshold, smaller is the affordance set size. So your affordances are smaller and more restrictive. So we observed that a smaller set of affordances leads to quicker learning and also gives a boost in the performance. Note that there is a 1-to-1 correspondence between the threshold, the affordance set size, and the success rate on the taxi task. So these results here show that affordances can indeed be learned online for a predefined set of intents and result in good performance. To better understand the impact of affordances on sample efficiency for the performance we just reported, let us now visualize the same results, but for the affordance set size being learned over time in the same pipeline. We start by assuming that all options are always affordable, which leads to roughly a huge space of roughly 38K state option pairs. The threshold again here controls the size of the affordance set, where larger Ks result in more restrictive and smaller sets. And as the learning proceeds with increasing amount of data, the affordance set size gradually decreases. So the agent initially thinks that everything is affordable, and over time it's able to learn that fewer and fewer things are affordable, leading to restrictive sets. The learned affordance set for the passenger-centric intent to drop off at destination is of size merely 2,000 state option pairs, which is even smaller than what we could come up with heuristically. So knowing which states afford which options rapidly improves the sample efficiency. So note here on the top left that the most restrictive affordances, that is the one agent, the baseline that knows what's affordable, is able to converge in only 10 million steps in the environment steps. Whereas when you compare it to the agent which assumes all actions are always available, requires around 40 million steps and is still struggling to fully converge. Finally, we quantify the gains in planning efficiency during the two-step process of model learning, followed by the process of planning. So in the legends, what you see here is the first step where what you used during the model learning process. Did you build a full model that is everything, or did you build a partial model that is informed by affordances? And what did you use during planning? Did you plan over everything, or did you plan over your knowledge of affordances that you have learned? So we report the number of iterations on the y-axis that are required for planning against the environment steps, and we observe that learning a partial option model requires fewer samples as opposed to learning a full model, which is not very surprising, and it just corroborates what we saw in theory before. And using affordances during both model learning and planning is most valuable, as opposed to learning a full model everywhere and planning with, which is very hard and it's expensive and requires much larger amount of data. So to conclude, we presented notions of intentions and affordances that can be used together with options. We provided theoretical guarantees for faster planning and improved sample complexity of building more precise transition models. And we showed that learning affordance-aware models online and planning with them can result in improved empirical performances. So again, what are the implications of doing this? That we have RL agents that can have the ability to represent world knowledge in form of partial models across many different timescales. And moving from one-step to multi-step partial models leads to further gains, but it does come at a cost. And the cost is of making an assumption and approximation of the intents that are being specified a priori. So looking ahead with these three pillars of foundations, I would like for our agents to be able to continually adapt and become better learners over time, the hallmark of natural intelligence. And one immediate promising direction in this pipeline is to relax the assumptions that intent completion is programmed by hand or by a designer. So one might instead consider leveraging structural priors to generate intention labels. So like I was saying before, examples of such structural priors include progress functions, such as temporally progressing, which is very easily available for free while you're taking steps in the environment. Navigational intents or information seeking intents can be included in different form of contrastive losses and so on. So another useful route is to exploit any access to humans in the loop, for example, for making few short queries of what an intended consequence looks like, or even for evaluation, eliminating the need to use a simulator. Finally, towards the goal of truly continually learning agents, I believe that a very important direction is to enable adaptive control by rethinking the agent-environment interaction. So to achieve this, our agents need to actively build tools by leveraging the internal models of previously acquired knowledge, which will allow them to navigate in the affordance landscape. And it will allow them to shape it as well. So for instance, if I want my agent to learn to navigate and pick up objects, over time, I hope that it's not just limited to these two skills or these kind of knowledge, and it's able to do more things and eventually build tools. So for instance, if I have learned to pick up objects or grasp objects, over time, I hope that the agent is not just able to do tool use, but to also build tools, such as learn that if I pick up a tray, I can actually use it as a tool to carry more objects. Or if I pick up a basket, that can be used as a tool. So all of this would require our algorithms to model different types of non-stationarity and to really rethink the agent-environment boundary, as it is not as stationary and static as it has been in our textbooks. And finally, leveraging these ideas to be able to learn and plan at scale has the potential to address limitations of the current system. So for example, the latest advancements such as Robotic Transformer 2 also have these limitations where the skills of the robots are limited to what was seen in the training data distribution, and the computational cost during inference time is really high. So these ingredients of selective attention through the lens of temporally extended affordances has the ability to capture underlying invariances, build partial models, such that we are able to plan and learn in a way that provides computational gains, especially in the low data regime. And none of this would have been possible without my wonderful collaborators. From these works highlighted here, there are many more, and all colleagues at Mila. And thanks to people who gave feedback for this talk as well. Yeah, I'm happy to take questions and anything you have. Yes.
Yeah, I had a question on the sample complexity that you showed. So you showed that you showed that in the middle of the slide is bound that scale is the size of the state, size of observation, or size of option space, and then you could get that down to the size of the affordance set. I guess I'm curious because my understanding is like you're learning the affordance set. Is there sort of, are you paying sort of a size of option space like in a lower order term somewhere to learn the affordance set, or are you able to get rid of that completely?
I think we don't account for the learning part here.
I see. So
Yeah.
this is just assuming you have the affordance.
Exactly.
I see. Okay.
Because you have learned that, let's say, through a classifier, and now you're building a model.
Right.
The sample complexity here for each, if you were to make a fair comparison, if I understand or remember correctly, this has been a while since this work, but I remember correctly is that you are using only making the sample complexity bound when you're building the model. So whatever you did a priori is a priori. You have the affordance set, and now you're building your sample complexity bound on that affordance set of learning the transition model. So how many samples do I need when I'm learning a transition model? So if you're learning a full model, you need to look into everything.
Do you have any sample complexity analysis on learning the affordance set?
Not in this paper, no. But I think that'll be very interesting to look at both happening at the same time. Yeah.
Okay. Thank you.
I guess last chance for questions.
Yeah, and if anything comes up later too, I'm actually based here in Seattle, and I'm on Slack. I attend weird lab meetings, so feel free to reach out.
I'll ask one question. So this is pretty cool results. Like, I guess coming from a robotics perspective, where do you think this could be most like immediately applicable? Like, given the models that we have, and like how hard is it to learn from like real world data?
Yeah. So the more and more I engage with the robotics plus RL intersection, I think there's a lot of things that are already being used in sense of affordances. So there's a lot of like success classification happening where you have a trajectory and you either ask a user to tell you whether the success was made or not, and you use it back to like learn a classifier that tells you what was successful. So the way I see it is like there's a lot of work out there which is using one form or the other of how we frame and formulate affordances. And it's just nice to see and get that reinforcement that we have nice theoretical guarantees on why it works and making that bridge on why it works. And I think like in general, any problem where you have little data, but you have a huge branching factor of like action spaces to consider, which is usually the case in any real world robotics, this will be very beneficial and it will be good to explore directions in that sense.
So you said actions, from what I understood, were that you're considering trajectories over different horizons,
Yes.
right? So instead of single action, you're considering like 2 actions, 3 actions, and so on. So in the work that you've considered, is everything deterministic, or do you consider?
No, it can be stochastic. Like your P can be actually stochastic. The transition dynamics can be stochastic.
So learning affordances came up a minute ago. Is that something you plan to work on in the future?
Yeah, so I'm looking for like different ways to, so definitely scaling up things that we talked about today, and maybe looking into more continually learning systems, so not just limiting to an offline data set. So if you have learned something to begin with, or you have no data set, then how do you adapt your affordance like landscape? That's something I'm definitely very interested in, yeah.
All right, last chance. All right, thank you very much.
Thank you.